Everyone, and welcome to this explainer. Today, we're diving into something really exciting. We're going to be exploring a profound structural shift that is happening right now in artificial intelligence. Seriously, this is a massive evolution. We're talking about the transition of AI from spatial geometry, which is basically how models organize data in a static, frozen moment, into temporal pathways, meaning how these systems actually move, adapt, and maintain their stability over time. It is an absolutely fascinating journey. And honestly, understanding this is going to fundamentally change how we think about machine intelligence. We're watching it shift from what is essentially a fragile, albeit brilliant tool into a durable, foundational piece of infrastructure. So let's get into it.
Okay, let's just dive right into the core of the issue with a question. If modern AI can instantly organize basically all of human knowledge, why does it still lose the plot over time? You know exactly what I'm talking about, right? We see these incredibly powerful large models that can do it all. They write essays, they generate stunning images, they synthesize complex topics in seconds. But when you ask them to maintain an output across a really long time horizon or track complex causal chains, they start to stumble. They might completely contradict a premise they established 5 minutes ago. They shift their narrative assumptions, or they just spit out conclusions that have literally no grounding in reality. They lose the plot. And why is that? Well, because as utterly brilliant as they are probabilistically consistent, but they lack long-term causal direction. They know statistically what word usually sounds right next, but they don't necessarily know where the entire train is heading.
Now, to really understand why this happens, we kind of have to look back at how we got here in the first place. And that means focusing on the monumental work of Yoshua Bengio. So before Bengio, the absolute central problem in machine learning was what we call rule construction. This was the past. Engineers had to painstakingly manually tell the computer exactly what to look for. They had to code what a line was, what an angle was, what a specific audio frequency was. The AI's capability was 100% dependent on explicit human-coded engineering. But then Bengio completely flipped the script. He sparked this massive breakthrough that we now call representation formation. He moved the entire AI paradigm away from human-coded rules and pushed it into this amazing realm of self-organized internal encoding. Suddenly, we weren't manually defining the features anymore. Instead, the neural networks were constructing their very own internal coordinate systems directly from the raw data itself.
And that brings us to a really foundational concept here, representation learning. This is the actual process where models compress massively complex, high-dimensional data into these beautifully structured latent spaces. Think of it like a vast, multidimensional digital map. Every single word, every image, every little sound segment is transformed and assigned to a very specific location within this space. And the magical result is that similar objects naturally cluster together geometrically, while dissimilar objects get pushed far apart. This breakthrough was a total game changer. It meant AI was no longer just a simple rule executor following a script. It became a representation-forming machine. Its capabilities weren't bound to just one specific task anymore. Instead, its power became bound by the actual structure of that newly created geometric space.
So what is actually happening under the hood? Well, this structural compression works through something called layered abstraction. You start with high-dimensional inputs. We're talking about raw pixels from a camera or audio amplitudes from a microphone. Initially, these inputs just have massive numerical variation, but absolutely no explicit structure. It's just noise. The network takes that and reorganizes it layer by layer through nonlinear transformations. The early layers might pick up on really simple patterns like edges or color gradients. Then the intermediate layers start combining those into shapes. By the time you get to the higher layers, it's encoding full, rich semantic concepts. And this whole shebang is driven by backpropagation, which is essentially a continuous feedback loop that adjusts internal weights based on errors. It just keeps nudging everything in the right direction until, ultimately, you get this perfectly organized embedding space where all those similar concepts beautifully and neatly cluster together.
Now, Dr. Wesley Shu frames this whole representation process in a really fascinating way through what he calls the energetic paradigm. He describes this process as energy compression, and I love this analogy. Think of it as a continuous flow. First, you have this raw, chaotic informational energy entering the system. Next, the network's layers act like a massive filter, dramatically reducing redundancy through that layered abstraction we just talked about. Then, all that chaotic data is stabilized into those lower dimensional latent structures. And the ultimate result? The computational efficiency per unit of energy just absolutely skyrockets. This structural compression effectively shortens the distance between raw, unorganized, messy data and highly refined, hyper-capable AI intelligence. It is incredibly efficient.
But here is the catch, and it's a big one. While representation learning is absolutely incredible at spatial restructuring, it carries some major systemic blind spots. On the left side, we have its strengths. You get phenomenal statistical compression and incredibly efficient geometric manipulation. Basically, doing tasks in AI right now is just doing vector manipulations inside a static geometry. But look at the right side. The blind spots are severe. There is zero automatic causal continuity. The system struggles hard over long time horizons. Why? Because these systems are probabilistically consistent but causally blind. They can organize correlation patterns beautifully within space, like drawing an impossibly perfect, detailed map, but they do not automatically impose causal continuity across time. It's the difference between having a perfect map of a city and actually knowing how to safely drive a car through its rush hour traffic without crashing. And this leads us directly into a really dangerous spot that we might call the geometric trap. You see, representation learning rewrites space brilliantly, but it doesn't inherently encode things like delay, accumulation, or irreversibility. Because the model is entirely focused on optimizing probability distributions rather than understanding real-world causal pathways, its incredible efficiency actually ends up amplifying its systemic fragility. The more capable the model gets, the more energy density we have in the system, which amplifies its potential impact. But, and this is the crucial part, that compression provides absolutely no intrinsic guardrails for long-term stability. So compression accelerates capability, sure, but it leaves the entire system incredibly vulnerable as time unfolds.
Which brings us to the exact limitation where representation learning basically hits a wall, and where a completely new paradigm has to begin. As Dr. Wesley Shue so perfectly puts it, representation forms space, EP designs path. I want you to really think about that for a second. It's a simple quote, but it's an incredibly profound distinction. Representation gives us the space, it gives us the map, the static geometry of how all these different concepts relate to one another. But we need a way to actually navigate that map over time without the whole system breaking down. We need path design. Enter the energetic paradigm, or EP for short. EP is a new framework that essentially extends our structural analysis of AI away from just looking at spatial compression and pushes it directly into the temporal dimension, into time. It begins with this foundational premise that organized systems have to be evaluated through how energy flows across time. So, where representation is busy compressing geometry, the energetic paradigm is busy formalizing causal pathways, delay structures, and steady-state transitions. It is literally the necessary solution for opening up the dimension of time in AI architecture, which finally allows the system to understand things like consequence, duration, and long-term stability. Now, what's really interesting about this is how it breaks down into 4 main pillars. And to be clear, these are not just optional, nice-to-have regulatory add-ons. These are complete structural redefinitions for how AI operates. First, we have load accumulation. EEP treats load as an accumulated quantity over time, meaning it recognizes that even if an AI system looks totally fine and stable in the current moment, hidden stress might be secretly building up to a breaking point. Second, we have to view delay as risk. Deferred consequences actually store energy, and if a system ignores that, that energy can release abruptly and chaotically. Third is causal transparency. This demands actual cross-temporal integrity. The AI has to be logically consistent across time, not just highly correlated in one single isolated snapshot. And finally, steady-state detection. This is the ability of the system to actively identify irreversible transitions before a complete catastrophic systemic collapse actually occurs. To really wrap our heads around this, we have to contrast how we traditionally think about these systems versus how EP demands we think. Right now, so much of our engineering analysis relies on what we call equilibrium grammar. And this basically assumes that if an AI system experiences a bug, a disturbance, or an error, it can easily just bounce right back to its prior stable state. No harm done, right? Well, EP replaces this completely with path grammar. Path grammar recognizes that the real world has strict thresholds. Think of it like shattering a glass. Once you cross that specific threshold, returning to the prior state is physically impossible. The glass is broken. This is a massive, fundamental shift. It demands that AI architecture finally processes the strict reality of delayed consequences and true irreversibility. So if we distill all of this down to its most concise, absolute core summary, it looks like this. Representation increases efficiency. EP manages systemic risk. They are completely distinct concepts, yet they are utterly complementary to one another. Yoshua Bengio's spatial compression is what gives the AI its mind-blowing power and speed to understand high-dimensional data in an instant. The energetic paradigm's temporal design is what ensures that this massive, almost incomprehensible power is actually directed safely, stably, and continuously across time, making sure we don't accidentally shatter the glass. And this synthesis really builds a clear, undeniable roadmap for the future. It highlights an evolutionary leap that we have to make, going from statistical learning over to dynamical system learning. Statistical learning, as we've seen, reorganizes correlations. Its vector space is entirely static. It writes geometry.
But dynamical system learning reorganizes energy sources. It doesn't just sit in a static moment, it unfolds through time, and most crucially, it writes causal direction. Right now, contemporary AI research is heavily concentrated on spatial engineering. We're talking about attention mechanisms, deeper embeddings, larger context windows. But long-term path stability? That remains dangerously underdeveloped.
So what does the synthesis for future AI actually look like? What are the requirements? Well, to maintain real cross-temporal integrity, future systems absolutely must combine Bengio's spatial compression with EP's temporal path engineering. There is no either-or here. This means we have to start embedding principles of energy conservation directly into the model's architecture. It requires implementing strict load transfer rules, so the system actually knows how to safely handle accumulated data and the consequences of its outputs over time. And it absolutely unequivocally must feature irreversibility detection over long time horizons, so the system never accidentally blindly walks across a threshold into systemic collapse. Every single one of these components is a vital, non-negotiable necessity for the next generation of machine intelligence.
Ultimately, the big takeaway here is that artificial intelligence has to move from being just a really impressive statistical capability toward true, durable infrastructural stability. By adding these dynamic, time-based constraints, we fundamentally transform what AI even is. It stops being just a simple representation transformer that operates in isolated, disconnected snapshots of space. Instead, it evolves into a dynamic structural model of energy pathways. It becomes something that is genuinely capable of safely maintaining its logic, holding its narrative, and guaranteeing its safety over prolonged, continuous, real-world use.
Which really leaves us with what I think is the most critical question of this entire technological era. Will future AI remain just a fragile compression engine, highly efficient, incredibly smart in the moment, but easily broken over time? Or will we successfully engineer it into a durable, dynamic, energy-ordering layer for our incredibly complex world? This shift, going from spatial representation to temporal path design, it isn't just a cool feature upgrade, it is an absolute necessity for the survival and viability of future intelligence. Thank you so much for joining me to explore this massive paradigm shift today. It's a lot to think about. Keep learning, keep questioning, and keep looking closely at the structures that are shaping our future.